All right, thank you. Like I said, my name is John Askew. I'm super excited to be presenting Pass It On, Lessons Learned from Building a Game Proxy. It's an honor to be speaking here, and thank you all so much for your attendance today. As a thank you, we're giving away a Nintendo Switch Lite, so if you're interested, please follow the QR code on the slide to the sign-up form. I'll leave it up for a few seconds. And no, this is not a live hacking demo. There are no exploits in that QR code or on the Microsoft Forms site, at least to the best of my knowledge. And I'll put it up again towards the end if anybody misses it. No? All right, my apologies. We'll get that sorted and then we'll post it on the Discord or somewhere else. Okay, so this is me in a nutshell. Well, actually, this is me in polygons. This is me in a nutshell. Like many of you, I enjoy building things and breaking things. Most of all, I really love learning new things. There's always a ton more to learn in this field. I have worked in offensive security testing for 15 years. And to be honest, I'm starting to think this imposter syndrome stuff never really goes away completely. I'm a consultant at Dean Dorton, where I get to work with a great group of security folks. I also have a side business, Terrapin Labs, where I do research, training, and other side projects. I'm bad at social media, but you can find me on Twitter, GitHub. I stream on Twitch, usually Thursday evenings. Occasionally, I even have a viewer or two. Fun fact, most of my proxy that I'm going to talk about was written live during those Twitch streams. LinkedIn, sure, why not? And of course, please feel free to come up and chat with me about this presentation or, guitar or backyard hydroponics, whatever. That's why we're all here today. Since your time is valuable, let me help you try to quickly determine if you should stick around or track hop or head down to, the saloon or Starbucks or whatever. This talk might be for you if you're curious about thick client network application security testing and reversing. Maybe you've got some experience with web application testing and you're curious how those concepts might apply to non-browser-based applications that may or may not use HTTP. We're going to basically be using a lot of the same techniques to look at a game. This talk might also be for you if you're interested in real-world examples of building reverse engineering tools, particularly network-based tools written in Rust, because that's what I did. I wrote a tool for inspecting game traffic. This is not a talk on Rust programming. Don't let that scare you. I don't expect you to have any familiarity with the language, but I may highlight some concepts that make it nice when developing these types of tools. You might like this talk if you appreciate hearing about failures as well as successes. I think we talk a lot about successes and don't hear as much about the failures that those successes are built on top of. So I'm going to attempt to do that. Although I may fail at that as well. And this talk may be for you if you enjoy dad jokes, awkward or misplaced cultural references, and weird metaphors. If that kind of stuff's distracting to you, I apologize, but it helps me get through the presentation. And there might be a little surprise at the end, but don't stick around just for that. All right, this is the roadmap. We're in the introduction. And we're going to talk about let's get hacking, how to begin a project like this. We'll go through parsing, the importance of taking packets, turning them into protocols. We'll talk about handshakes and trust, those authentication, authorization, encryption pieces that all modern protocols will involve. We'll talk about layers, how we put different pieces together in a kind of a layered format. We're not talking about onions and ogres, but I can't say layers without thinking of Shrek for some reason. We may pause briefly for questions if we've got time, and then end with a call to action. So the number one lesson learned was to embrace failure. Thank you for coming to my Wild West Hackin' Fest talk. Now, in all seriousness, this slide can cover a fair bit of ground for the presentation, and it works on a couple different levels. We could talk about, at a technical level, approaching building tools from a kind of failure-driven development. We could talk about specifically stuff like parsing, how We write parsers with the expectation of failure. But really, as a whole, this presentation, I think, is a bit of a failure. I had originally intended to take some tooling and then explore some different games and maybe find some interesting vulnerabilities or quirks with them. And I did not end up getting that far, but I'm still presenting anyway. And I think we've got a whole lot of good information to talk about anyway. And that happens to me a lot. I tend to hit a point where I get stuck, and then a lot of times I'll move on to something else. So I'm trying to be a little bit better and release things, even if it's a little bit uncomfortable. With all that said, let's get hacking. So our journey begins with a game called Valheim. Is anyone here familiar with it? Okay. Yeah, Valheim is a Viking-themed multiplayer survival and crafting game in which you play as the spirit of a fallen Viking warrior who has been transported to the afterlife by a giant crow. Normally, if you'd want to commune with a Viking spirit, you would need to procure a Norwegia board and have a seance. But the fine folks at Iron Gate Studio have definitely made this experience accessible to the wider public. Why did I pick this game to study? Well, 2022, it's a good year for trying new things, changing things. I wanted to try doing some reverse engineering and hacking on a live stream. Obviously, it'd be problematic to do any kind of customer application in that scenario. I was playing this game at the time with some friends, had a self-hosted server, so I could set up a good test environment, and the multiplayer game seemed like a fun target. I might see some stuff I wouldn't normally see in like a business application. And the fact that I knew a few Viking puns may have played a part as well. So when we're starting, we should always start with a driving question, so we have something to focus on and make the most use of our time, which is usually going to be our biggest limiting factor, time. I'm very not naturally inclined to think about time tracking, but if you don't take ownership of your time, then that's how you come out of a trance to birds chirping outside your window, realize you've played Civ 2 all night and have to be somewhere in an hour. Core memory. So for this project, I'm going to start with a question: how does the Valheim server password get sent? And of course, this question can change and evolve as we go. We can also approach reverse engineering for a number of different angles because we have a lot of different types of analysis we can do. We can do static analysis, dynamic analysis, log analysis, which is underrated, network analysis, where we purely look at the network traffic and try to discern things from that. Paralysis analysis, where we perform analysis to make sure all these choices that we have don't cause analysis paralysis. There's no right or wrong answer here, but I like to start with looking at network traffic, so that's what I did here. Here's some tools that I used, and I'm going to use pretty standard for the most part, and the tool doesn't matter so much as the techniques that you're using, so feel free to insert your favorite disassembler and your favorite debugger or binary. But then when we reach the point where our tools can't do what we need, we're going to attempt to build some things of our own. And in this project, I started off with some one-off scripts in Python, eventually moved over to a bigger framework in Rust. So just be aware of that when you see two different types of programming languages in the slides. So let's start by capturing network traffic between the Valheim game client and our self-hosted server, which goes over UDP 2456. Since Wireshark does not recognize this protocol, we're going to use one of the oldest reverse engineering tools, our eyes, and look for patterns. So in this packet capture, we see 4 different packets exchanged at the very beginning. And then after that, we're followed by a bunch of other data that appears to be some kind of encrypted payloads. So just using our eyeballs here, the first 4 packets we see start with a different byte value, and there's a pattern. Hex 20 for the first one, 21 for the second one, 22, and then 23, or 32, 33, 34, and 35 in integers. So we can search the internet for those numbers and see what we find. And after a bit of searching, we found something that fits on GitHub. This is a Google protocol buffer definition file with those same magic numbers, and they appear to correspond to control messages for establishing an initial connection. So bingo, we found it. Or as the Vikings say, bingo. It was pretty straightforward to figure out, all things considered, but that's not always the case when we're looking for stuff. Sometimes you might have to delve much deeper, where forgotten horrors lurk in old specifications, product manuals, software patents, so on. But here we're pretty lucky. We've got documentation as well as source code for Valve GNS. So this is a transport layer that is built specifically for games. It was originally part of the Steamworks SDK, which is closed source, but then Valve pulled out their Steam sockets, open sourced it, and released it. But it's still the same code base in both places. It's used pretty heavily in Valve games and a number of other third-party titles. And we also found that in 2020, some people at Checkpoint Research found a few CVEs, and that those bugs got fixed, but that's another source of information that we can use from their write-up. So we've got actually a good bit of information to go off of without doing any other analysis other than looking at network packets and searching for things. Now that we have a name for what we are dealing with and some documentation, source code, how do we start getting more familiar with the protocol? I personally like to start by writing a custom client. And that can be as simple as just a tiny piece of code that replays some traffic that we've already seen. You do that a couple of times, you see what does the server send back, does it change? And then as we go, we can modify some of the bytes to see if we get a different response. We can look in those bytes to see if there's anything that looks like a noun, like an identifier or a name or something. We can look for other things that look like verbs, actions, or methods. If we change some of those things, what does the response do differently? Does anything happen out of band? And this is an iterative process, right? As you learn more things, then you can go back and add more things to your client. You can send different types of messages maybe, or different values that may be valid. So here is a screenshot of the original Python replay client code that I started with in this project. Like I said, I just copied the bytes straight out of Wireshark for this first packet and began replaying it. And I started iterating. I tried to figure out what I could discern from what came back. And you can actually get pretty far with this approach, and you can potentially learn a lot about the protocol, but eventually you're going to get tired of dealing with those raw bytes. So if you want to scale your project up past a certain point, like I did, you're going to need to abstract those raw bytes and start thinking in terms of structured messages. And that's where parsers come into play. So parsing is just taking the unstructured data and applying a structure to it. Specifically here, parsing network traffic is taking a stream of bytes and turning it into values and messages. And this is something that you're doing even if you don't realize it. If you're dealing with network traffic, you're doing some sort of parsing. Either some parser already exists that you're using, or if it's an unknown or unfamiliar protocol, you might be writing your own. You might be writing an ad hoc parser, which is just like I was doing originally, shuffling bytes around in Python, or maybe a more formal one using a framework. And after doing it both ways, I feel like in the future, I'm just going to embrace parsing with a good library or framework from the beginning. And also, in my opinion, frameworks that support parser combinators are my preferred way to go, which are basically combinators of tiny little functions that parse individual values, and then you compose them with other parsers and you build it up like Lego blocks to a whole message or set of messages. And if you're using Rust, then I recommend using the nom crate for network parsing. So try to put take this from the abstract to a little bit more concrete. This is how you might parse that challenge request message that we just showed that gets sent. Ignore the fact that at the bottom we've got this Google Protocol Buffers library doing the heavy lifting with the parse from string method. But initially, we are matching the first byte of our incoming byte stream and looking for that hex 20 message type, the challenge request type. And then if we hit that, then we're slicing out a couple bytes, turning them into a length. Then we're taking that length and we are pulling more bytes out from another slice and feeding it into our parse from string method. And this works, but it starts to get awkward pretty quick in a project like ours, where there ends up being a lot of message types and they're nested inside of other message types. And we're trying to match it all with a big spaghetti of if-else statements. That's before talking about Python's type system. No offense to Python fans. I do like Python. But I think a much better approach is to write declarative parsers using a parser combinator library, which at a high level, instead of writing a procedure for parsing, where you're saying if this, then this, else, and it gets pretty complicated. We are letting the framework handle a lot of the tedious stuff like buffering and cursors and things, and we're just writing what the messages look like. So the challenge request here at the top, this is just a delimited message with first a tag identifying the message type, followed by a payload that has a length at the beginning. And then at the very end, we've got a bunch of null byte padding. We're just using this combinator called rest to take the rest of it and throw it away. So that's how you parse that one message. Then at the bottom, you have an alt combinator that makes it really nice to parse, to put multiple parsers together when you know that you might get one of several different types of messages. And our end goal here is basically having a suite of parsers that compose well together like this, and they're pretty straightforward to test. Now, understanding the structure of a message, what can we do with that? And it's really surprising how much you can do to an application just by being able to send and receive structured messages even before any kind of authentication. For some protocols, you can find interesting or sensitive data just being transmitted just by getting over that initial obfuscation hurdle, being able to parse the raw bytes and understand it. You might also be able to craft some messages that elicit information like the software version strings, or in a game, the player counts. That's something that easily get a lot of times. One thing in particular that I like to do with new protocols is find a way to discover content with some basic fuzzing. And that's basically, if you think of in web app testing, something like Dirbuster, where you're fuzzing URLs, but for non-HTTP protocols. And I think a good timely example of this, you may have heard recently this LDAP Nom Nom project on GitHub by Lars Carlsland. Just by understanding how these connectionless LDAP messages work, we're able to do unauthenticated brute force guessing for valid Active Directory usernames, and doing that very rapidly, actually. Another good example, let's just take a brief detour. I was recently doing an application test on an application running on top of WebSphere app server. We'll just call it ACME web server app. It was a zero knowledge kind of test, and there weren't a lot of interesting services running. We had SOAP services, but there were no management interfaces, no interesting URLs we could find, and any of the SOAP messages required authentication, which we didn't have credentials for. We also had these Corba IOP services, and I didn't know what exactly was going on with those. We tried some existing tools and they didn't work. There's an nmap NSE script to gather information from the IOP name service, but it wasn't working. I did a whole lot of reading, and I wrote some Java code, and the Corba library that I was finally able to get working didn't support TLS. I set up my own test WebSphere server. I disabled the TLS requirement on the Corba interface in WebSphere, and then I was able to get that crappy Java code that I wrote to run against it, and then do packet captures of my own, client, Java client. So from those packet captures and reading some old Corba specifications, I wrote some parsers. Now I could begin crafting GIOP messages to send to the server however I wanted, whichever port I wanted, plain text or on TLS, and Java can no longer tell me how to live my life. We ended up being able to actually gather some useful information from the Corba name service, although I do want to look more into this in the future. Unfortunately, with Valve's GNS, there's not a lot of interesting things we can do up front. We can send and receive these control messages, but we don't know how to encrypt or decrypt the data messages. And that's where our target data is being transmitted. And even if we were able to drill into the data, we can't do our replaying stuff, right? We don't have any examples of what the client is sending to the server unencrypted. Ideally, we'd be able to see both directions, right, between the client and the server unencrypted. So if this was a web app, what would we do? We'd grab a proxy like Burp or Zap or Paros. So yeah, that's what I decided to do. Going to try to write a proxy. Seems simple, right? And we're doing this because we need some capabilities. We need to be able to inspect what is being sent and received. We need to be able to, maybe in the future, we might want to manipulate those messages, change them as they go back and forth. And we want to be invisible to the client and the server. We don't want to impact their behavior. We kind of want to observe them in the wild. You can accomplish this through other methods, like process injection on client or the server. But a network proxy really gives us what we need with a lot of power and flexibility. We can run them on the client. We can run them on the server. We can run them anywhere in between. We can even chain them together with other proxies. And this is part of why using a proxy in web app testing is so powerful and so ubiquitous. Also, we don't have to worry about endpoint controls. A lot of game hacking tools tend to focus on process injection and memory modification stuff, but then they have to deal with the anti-cheat code on the client. And you might note the strong parallel here between red team tools and avoiding EDR. Side note, red teamers, you can learn a lot about low-level Windows programming and evasion methods by looking to game hacking forums, if you weren't already aware of that. Plus, I just think they're neat. I wanted to build a proxy, see if I could. So in the novel Children of Ruin by Adrian Tchaikovsky, and minor spoilers ahead if you're planning on reading this book, just close your ears for a second, we encounter an alien life form that is able to inhabit a human brain, specifically in the corpus callosum, which is what connects the two brain hemispheres. And we get to read a little bit of internal monologue from this alien. We listen, information on either side of us. And what have we found? We cannot know, but we store and process, construct our theories and our models, careful not to upset the balance. Each pattern of information that comes to us is examined and passed on, one side to the other and back. So I was reading this book while working on this presentation, and I thought I was having a mix-up here for a second. I was pretty surprised when the author started to describe what is essentially a man-in-the-middle proxy, just a biological one. And of course, this alien parasite eventually learns enough to start tampering with the data. One generation begins to change the information as it passes through us, inserting our own data, modifying its own parameters, speaking to it in its own voice. So that's pretty creepy, right? But I think it describes the power of a proxy quite well. And it's also relevant for one other reason. Outer space is basically the Wild West, right? And this alien has clearly performed a hack infest. All right, yeah. There were a lot of people that had an opportunity to review the rough draft after this presentation over the past 2 weeks, and nobody told me no, so that's on you. We're going on an adventure to build a proxy. If you have read the book, you know this quote, and it is not the Bilbo Baggins meme from the Hobbit movie. But before we can proxy traffic, we have to unwrap that encrypted data session. So let's talk about handshakes and more generally about trust. Now, I tried really hard to find a Viking joke that would be relevant here, but I came up empty-handed. Sorry. So at a high level, any cryptographic handshake is going to probably involve three things. First, we've got two parties that are going to exchange some parameters. Then they'll both do some math stuff. And then finally, they'll start sending encrypted messages to each other. If they did that math stuff right, then they'll be able to understand each other. So for our case here, we can ignore the first message pair, the challenge request and challenge reply, which are basically for DDoS protection. The real important stuff is in the connect request and the connect OK. And if we look into the fields of that connect request message, we've got two cryptographic parameters. There's a, y'all read that? It's kind of small, sorry. There's a crypt info signed field, which is ephemeral keys and crypto parameter negotiation. It says it right there in the documentation in the code. That's where most of our stuff's going to be. We also have this certificate signed field, which deals with identity, public keys, and potentially a signature from a certificate authority, which we'll get to later. If you look at the connect OK message that comes back from the server in response to this, has the exact same fields. So there's a symmetric exchange of parameters. So now we got to figure out which of those parameters go into the math stuff. And we're going to read more documentation. In particular, the README here has all of it laid out at least a high level. We're using Curve 25519 for key exchange and signatures. We're using AES GCM 256 for the per packet encryption. There's also a shared key derivation and per packet IV that reference Google's quick protocol design document, which I'm not going to make you read as well. But this should lay out pretty much which functions we need to look for in our crypto libraries to put this together. And yes, we've been doing a whole lot of reading. Sometimes reverse engineering is more reading and taking good notes than anything else. That is why the greatest Viking reverse engineer of all time was known as Eric the Well-Read. So reading the source code, observing those fields, in the exchange messages. This is essentially what we have to build. Those parameter exchange at the beginning, client sends, and then server replies. Then our math stuff, and then we start sending and receiving data messages. And there's the math stuff. We got a IKM that comes from an X25519 key exchange. We have assault and info values that we generate from this metadata from both of those messages. And then there's this HKDF function that generates our session key data. So that's a lot, but all these things are Googleable, searchable. You can find them in libraries. So we're just going to start trying. We're just going to start throwing stuff and seeing if it sticks. So like I said, at the beginning, I was using Python to try to POC some of this stuff. There's a cryptography library in Python that actually does all of these things. So we plugged them in, first attempt, complete fail. No big deal. Kind of expected that. I go back and find some typos, find some things that I did wrong, some bugs, fix those. Second attempt, fail. Third attempt, fail. I'm starting to feel like this. I don't know if you can see him at the bottom, this Age of Empires 2 villager who's hammering away, but the walls are just not coming together. It is his life. So why isn't this working is something that I said quite a bit during this phase of the project. And after a certain point, you realize you just can't make any more progress without some new information. So we've gotten pretty far with just the network data we observed and all that source code and documentation, although I'm pretty bad at reading C++ code. So maybe it's time to pull in some other techniques like static analysis, dynamic analysis, stuff we talked about at the beginning. So yeah, we did some static analysis of the server binaries, and we identified our target crypto functions, kind of like this encrypt function at the top. Then we can use the function offsets to hook those with some kind of dynamic analysis. And I used Frida, but you could use like a debugger or some other type of dynamic framework to inspect the running server while it's sending and receiving these messages. And this is really nice because with the math stuff, we had our inputs from the initial messages, and we had our expected outputs, which was those messages would be able to be decrypted between the client and the server. But there's some intermediate steps in there that we can't really validate. We just get to the end and it doesn't work. But with this, we're able to hook into that running process and find those intermediate values and then compare them. So instead of it being 10 or 12 different values there could be something wrong with, we can narrow it down to just the one that's causing us problems. And I found a bunch of more bugs that way. And then at some point in the process, I got lucky. I switched two parameters somewhere for some reason, and suddenly it all started working. So I went back. It was the HKDF. It was the first part of the HKDF. And I went back and reviewed the RFC for HKDF. And then I took a critical look at Valve's implementation. The RFC says in the extract step, the salt value should be used as the HMAC key, and the IKM should be used as the data. And of course, they were switched. Which, to be fair, that's normally how you would use an HMAC, is feed the crypto key into the key position. But there's a specific way that HMAC or HKDF does this for some performance reasons. I immediately thought, is this a vulnerability, right? Because you switch two important crypto parameters. That sounds bad, right? But reading this ePrint article at the bottom, this particular design decision of the HKDF, I don't think there's any security impact. It's really just, like I said, about performance. But if I'm wrong, please let me know. Would love to know why. So we're able to build a final implementation of our handshake. This is what it is doing currently in Rust. We've got a couple good high-level libraries for doing the key exchange and the message encryption, and then we had to write that custom HKDF implementation to be compatible with Valve. Oh yeah, what about the certificate signing we talked about earlier? So Valve lets you submit, when you generate a certificate for this connection, it lets you submit it through the Steam API to get it signed, and that basically authenticates your connection to your Steam ID. Well, according to the code and the documentation, It's up to the application whether they want to implement this or not. So I'll give you one guess as to whether they implemented this or not in the application layer. They did not. So at this point, we have enough pieces to finish a proxy and start passing traffic. Just to step back for a minute, we've got our downstream handshake that we do with the client, where the client thinks that our proxy is the server. We do another handshake upstream with the end server, where it thinks our proxy is the client. So then we've got two negotiated sessions. And then whenever a message comes in from one side, we decrypt it with that session key. We can inspect it, and then we can re-encrypt it and send it along. And this actually worked pretty well. Here's the Rust code of our minimum viable proxy, which isn't doing anything other than decrypting, re-encrypting, and forwarding. We basically got two Tokyo tasks, which Tokyo is just the main asynchronous framework in Rust that you use most of the time. We've got two tasks that one handles one side, one handles the other. And like I said, they just decrypt and re-encrypt and send along. And the game runs fine. We did have to change a few things. We had to reset the flags field, and we had to change the connection IDs because they're specific to the connection. But other than that, worked great. Of course, we're not doing anything super interesting yet, but here's some implementation notes, some lessons learned here. We didn't worry about DDoS protection because we don't care. We're using this for research. We're not going to post it on the internet right now. We didn't have to submit certs to Valve for the CA signature because the application didn't require it, although I could anticipate looking at other games that do require that and then having to add that feature in later. We used high-level crypto bindings for everything except for the HKDF because it was non-standard. I kind of wish I hadn't done this whole process twice, but learned a lot. I would do the implementation a little bit differently if I had it all to do all over again the first time. A few other lessons learned: that dynamic instrumentation was crucial for validating those cryptographic values that were generated by the other side. It helped us really narrow down which of those intermediate math steps were correct and which ones we were doing wrong. Parameter ordering, obviously that was the big problem with the HKDF function. Be on the lookout for that. That could lead to bugs or even vulnerabilities. And I found that using unit tests to capture actual values from network traffic or actual values from the parameter exchange as input, and then being able to iterate using those unit tests was helpful as well. And it's also a good place here to start thinking about authentication and authorization. And I want to talk about another business app test that I did. We're going to call this ACME file service. This was an app with server and client components. It was file, create, update, delete kinds of stuff. Basically, think of SMB file shares, but its own custom protocol. The messages were encrypted. The mechanism for encrypting them was unknown. I basically used all the same techniques that we've talked about up to this point, like capturing and replaying network traffic, writing parsers, and hooking native functions or APIs to track those values, those intermediate values in the client application. Nothing really more sophisticated than that, and was able to determine that the client and the server were generating an encryption key insecurely from basically a static secret that was shared across all the clients and the server, and a random value that the client generated for each message. So the key is basically a combination of those two things. And you can probably see the problem here. Client's not a secret value, but it has the static secret in it. So you can obtain that easily, and then you can also obtain the other half by looking at the network traffic. So possible to decrypt any message that we see on the wire, and also to forge messages to the server without authentication, which this resulted in some pretty serious risk to the environment. Okay, so now that we can negotiate sessions, we can encrypt and decrypt that data and peer inside those data packets, those data messages. Unfortunately, what we see inside, there's still a lot more to do. It's kind of like those Matryoshka nesting dolls inside of nesting dolls, or you might have also heard the term turtles all the way down. It's not quite that bad, but there's a lot more to do. because this is like a sophisticated, this is an optimized protocol for games, right? So they're doing some interesting stuff. They're handling fragmentation, reassembly, retransmission. We've got reliable and unreliable message types. We've got some fancy ACK vector model, which has its own RFP. And then we've got other documentation from the Valve repository about this SNP wire format, which has 5 different additional message types. So we get to do more parsing. This one slide kind of summarizes the big picture here. We've got our GNS data message that's outer frame. Then we've got the encrypted payload that we're finally able to crack. Inside that encrypted payload, we've got different 1 or more SNP frames. There's ACK messages, there's stop waiting messages. There's also reliable or unreliable frames for different types of messaging. This is a Valve message, or Valheim message, and it's using the reliable messaging, which is more like a TCP stream. Note that the password there, or the password hash, is Hunter2, which is the password for my test server world. And you can validate that yourself by copying and pasting that into IRC, where it should show up as all asterisks. So we can search now inside that encrypted payload. We can search for values in the unparsed plain text, even inside the specific SNP segments. But because of the way this reliability layer works, there's a few problems. We're not guaranteed that the entire app layer message is going to be contained in a single GNS data message or a single UDP packet, right? As far as the game is concerned, it's just seeing a stream like TCP, and it can frame that traffic however it wants with no regard to how the Valve layer breaks messages up. So we've got these potential for breaking messages apart, which makes it tricky to parse how we have it now, the application layer. And because we've got that reliability layer, we can have things arrive out of order or even not at all and have to, ask for it again. The best way to inspect the app layer here would be to reconstruct the stream, but that would require implementing all of this reliability layer functionality. And that seems like a ton of work to me. If we brainstorm, just thinking about that, we got to add buffering for our segments. We got to track which of those segments have been received and which have been lost. We got to have some logic for sending and receiving ACKs and whatever these stop waiting messages are. We got to know when to forward on the buffered segments. There's probably a bunch of other stuff that I'm not realizing up front. And yeah, that seems like a lot. So good projects, you got to find some compromise. What is the good enough visibility where we don't have to worry about reconstructing the whole stream, but we can still get a good bit of information? I decided that maybe we can get a output stream of that reliability layer, but not worry about doing it in real time. Just continue to forward the packets along at the higher level. We'd still have to buffer the segments, but we don't have to worry about holding on to them. We can go ahead and forward them. We still have to track which segments have been received, but everything else we can just leave to both sides to negotiate themselves. So that's the plan going forward. But you're probably wondering, did we find anything out about Valheim? What did that application layer look like? There's an SNP reliable segment there. A lot of dots and dashes. So obviously this is Norse code. Now, it's actually a custom built thing. They call it internally ZNet or ZRPC, and they send messages called Z packages. It's pretty straightforward. They've got a length prefix message, 4-byte 32-bit integer. And then after that, they've got a 4-byte hash of a method name. Like for instance, here, you probably can't see the very bottom of the screen, but there's a peer info method. So there's 4 bytes and then 4 bytes for the method. And then everything else in the message up to that length is part of that peer info or whatever RPC call, different parameters. I haven't made it much farther than this at this point, but we did learn a lot. Big thing here, I think, is understanding which layers you want to target and target those appropriately. If we were just Forwarding them on at a high level, we'd basically be routing, which is boring. I think our sweet spot here is forwarding on the decrypted messages like we've been doing and parsing out the internal frames and being able to spit those out for us to read. If we want to modify things for the reliable messages, then we're going to have to, that's going to be much harder. So we're going to punt on that for now. And then whenever we're talking about layers, we need to pay attention to where the responsibility lays for authentication and authorization. So I got one more example test application, Hackme widget orders. This is using a pretty complex stack of protocols. It uses Windows Communication Foundation. There's a binary protocol, MCNMF, also known as .NET Message Framing. It uses Spinego for handshakes or sometimes MTLM. And there's a binary SOAP encoding for the inner messages. I wasn't able to get through all of this at the time, but what I found out was that the application used the .NET message framing for authentication. So you have to do basically an NTLM or Kerberos authentication to connect. But then after that connection, the application code, it was the responsibility of the application code to check the identity if they wanted to authorize particular individuals. And they just hadn't implemented any of that. So you could authenticate to this service with any domain user and then do any of the functionality like create widget orders, change them, delete them. And that was pretty bad. And I think there's a lot more of this out there. So the completed code thus far is on my GitHub. You can find it there. Definitely a work in progress with a lot of rough edges. I hope that some of you might be able to use it as an example if you're interested in this sort of thing, or maybe you'll even look at some games with it. Whatever you do, if you do something interesting with my code, make sure that y'all holla at me. Y'all holla. That's what we call the Viking afterlife back in Kentucky. Oh yeah. So I really wanted to use this meme format I've never got to use before. And I know that maybe none of you would be that super interested in hacking on games. So I tried to find something else. And yes, Pip, in fact, we have written a second proxy. I went back and I cleaned up some half-finished code just so that I could use this format of a meme. You know, I have a podcast. Everybody has a podcast. So I'm releasing also NMF Proxy, which is a tool to proxy and inspect those WCF .NET message framing connections. It supports NTLM session decryption, although it's not currently working, but I'm fixing that. Spinego Kerberos is planned. All the usual disclaimers apply. Hope that you might find something interesting with this if you decide to. Okay, I think we got a minute or two for questions. If anybody has a question. Yeah. So the question was, what did you use to insert the proxy into the client and server communications? Well, I basically just, the proxy runs, you give it a listener IP import, and then you give it an upstream remote IP import for the server that you want to target. Then when you start up Valheim or whatever game, you point the game just at the proxy IP address instead of the server. And then because Valheim doesn't check the certificate signing stuff, then it all just works. Cool. Any others? And feel free to come and grab me around the conference if you want to chat. So the packet diagrams, that's my new favorite thing. That's Excalidraw. There's a website, and you can also get a plugin for Obsidian if you use Obsidian for note-taking. So I lean pretty heavily on that for this. There's the slides that don't work again. I'm going to find out what's up with that. Call to action. Now it's your turn. Okay. So if you would, I would like to close by challenging you to pick up a new project of your own, or maybe an old project that you've left. Hopefully I've shown a little bit that there's some interesting things you can discover just by digging into a new or unfamiliar network protocol, or even looking at familiar things in new ways. There's a lot of attack surface out there to explore. Just to rehash a few things we talked about. How do you eat an elephant? You probably shouldn't because they're an endangered species, but a metaphorical large problem like building a proxy, one byte at a time, just like you do parsing. Start with a specific achievable question, capture some network traffic, look for documentation or source code, find things you can modify and play around with, iterate as you acquire new information, solve problems, ask for help. That's a big one. I have a hard time sometimes asking for help or knowing when to, but don't be afraid to. If you got a mentor, that's great. You should start with them. If not, there's plenty of Discord servers floating around where you can connect with people and ask questions. The Wild West Hackin Fest server, Black Hills Knowledge Sharing. I think most of these guys have a server where they do that kind of stuff. Depending on the question, it might also be good to look to submitting a GitHub issue for a specific library or framework, or looking at mailing lists, things like that. I've found that if you show a little bit of effort, then people are often very willing to help out, even if they think you don't know what you're talking about. Most importantly, finish what you're working on. Don't leave it lingering. Now, this isn't meant as a criticism towards anyone. It's more as an encouragement if you struggle, as I do, with finishing things. Just find a good stopping point and share some knowledge with somebody else, even if you feel like it was a failure, because that's sometimes what we learn the most from. Write a blog article, release a tool or script. It doesn't even have to be sophisticated, Even just writing some notes up and then sharing with a coworker over lunch. It really helps to solidify your knowledge at a point in time that you can pick up later and maybe inspire some interest in others. Completing things is very hard, but you will be so glad that you did later. So one other speculative fiction book I read this year was Robert Jackson Bennett's cyberpunk disguised as fantasy novel, Lachlan's. Several points in the story, the main characters are discussing how monstrously difficult it is to build a new and freer type of society in the wake of collapsing totalitarianism. The quote that stood out to me was something, basically, that's how we know we're doing it right. Because it wasn't this easy, selfish accumulation and hoarding of power that had always failed in the past. It was this messy, hard work way that involved sacrifice, selflessness, sharing, and giving, helping others. In some ways, that may seem really cheesy and trite to take this lofty message of moral philosophy and try to present it, apply it to my silly side project somehow. But on the other hand, isn't that exactly what we're trying to do here today? Bringing people together to connect, share knowledge, and make us all better as a result. It takes hard work from each of us, organizers, presenters, volunteers, instructors, students, community members, everybody. So are you ready to put in the work to make this community great? If your answer is, I'm ready, then my response to you is, hi, ready, I'm Dad. That's the last one, I promise.